everybody, my name is Alberto Marquez. In this video we will discuss the fundamentals for simulation, particularly discrete event simulation. When we are performing a simulation study, we have to carry several steps in order to actually be able to build a model and solve a particular problem. These steps would be problem formulation, in which we define what is the system that we are going to study and what is the actual problem that we want to solve about that particular system. We have to define a solution methodology or follow a solution methodology. We need to narrow down the specifics of the limit of the system that we're going to model, as well as what parameters will define the system and other aspects of the simulation. So some of these aspects include the objectives of the study, the descriptions that we need, and how much detail we're going to have. If we want animation, what kind of animation and the level of detail of the animation. What are the inputs and outputs of the model, and what will be the project deliverables. In other words, reports or digital representation in the form of animations or 3D models, etc. So after we have defined the system and the specification, we proceed to create the model formulation and we construct it. After we have constructed the model, we proceed to do verification validation. We want the system to be performing to the logic that we want, and we want that logic to represent the reality of the system from a statistical perspective. Once we have a model that is verified and validated, we proceed to the actual experimentation and analysis on the performance measures and the parameters that we can change in the design of the system to try to solve the problem. Once we have a good solution, we present and preserve the results of the simulation, and finally we proceed to disseminate the model and the solution for different users to be able to make further analysis if that be the case. In a simulation study, we have goals, and while every project is different, we would like to have, or most of the time we have, the similar type of performance measures or goals of the system. And one could be estimate or optimize the total production. We would like to study the average weighting in Q. We would like to obtain the maximum time in Q, which is different from the average in the sense that maybe we want to minimize the bad experience for the product, or maybe some products could have expiration dates, and particularly having some waiting times exceeding a particular threshold could be an issue, even when in average it's okay. Those cases which exceed the threshold might be a problem. So a study on the maximum time in the queue would be important. We would like to have maybe a study on the average number in queue, or again a maximum parts in queue. So those are typical study goals. Of course, as I said, every project is different, and in some instances we want to know how many parts will be in the queue, because we need to prepare the space necessary to locate those in the queue and translate the number in queue into square feet or similar measures. When we are executing a model, a simulation, we need consistently several elements that will construct the model. The first one is entities. The entities are the particular elements that go flowing through the different stations, and they will usually represent the clients that go into the queues or are transformed in the machines, and eventually represent either manufacturing orders or actual products, and go through my manufacturing facility, or it's a paperwork that needs to be transformed and authorized and goes through different stages. All of these can be the entities represent all these type of situations. Attributes are tags that are attached to each one of the entities and give characteristics to the entity. If we would be represented humans in the system, and the entities would be these humans. Humans could have a different type of characteristics that could be relevant, and it could be for someone the weight or the height or the credit score or the amount of cash, the amount of cash previously spent. So in the case of a manufacturing part, it could be then the part number, it could be the next station in which it has to be transformed, it could be the color, it could be the order or the customer that will eventually receive that part. So these tags are associated to the entity and travel with the entity through the manufacturing process, but those tags could be changed as a consequence of traveling through the process. So one part after transformation could become in some different part, and therefore some of these attributes could be changing as they go progressing through the system. Resources are elements that are needed in order to have a transformation. The particular relation of resources in the system is that there is a limited amount of resources, and therefore as the entities go being transformed in the system or processed by the system, they may need some resources at some points, and because there is a limited amount of resources, the entities would have to wait their turn to grab the resource that is needed in order to complete the process. So if there is really no constraint in terms of a limited amount of resources, we don't need to model the resources. But if the entities will have to compete for an available limited amount of resources, then we need to model that by means of resources. Queues are the buffers where the entities come and have to wait their turn in order to grab one of those resources. It could be a machine, it could be a pallet, it could be waiting for some form of transportation, it could be the actual operator who will transform the entity into something else. As the entity is sitting waiting for their turn to grab a resource and be able to execute the process, that's what we have as a queue. We have statistical accumulators, which are special variables that allows us to compute the performance measures that we're looking for. We have global variables, which help to get some of these statistical outcomes, or they could be used to control certain functions in the system as a whole. These global variables will account, for instance, for the total number of entities in the system. And that is not particular for an each entity, is not particular for a resource, but it would be for the whole system. The statistical accumulators, on the other hand, previously described, they could be referred to, for instance, the total amount of time entities are spending in the system on average, or the one that has the maximum historically spent, how much time it has spent on the system, etc. We have the clock, and the clock has the control of the stream of events that will happen, and the clock advances from one event to the other in discrete event simulation. We have the initial conditions, very critical, because depending on those initial conditions, we will have or not to wait until the system is actually being representing the steady state conditions of the system. So if we start a simulation and the simulation has no entities in the system, we need to allow it to run for a little while before we can actually say, okay, now the entities have been flowing in the system and the queues are typical now, and we need to cut that, what we call warm-up period in the simulation. So initial conditions may determine some of these aspects in the simulation control. We have different type of statistics that we can use, and basically we can identify for the whole system, for the whole simulation, 3 types of statistics. One is a tally. A tally is just the summation of certain values. For instance, we can count how many entities went into a particular machine, or we can count how many entities travel through the whole system. It's just a counting process at a global status. We have entity-based statistics in which each entity will have its own data. Just like, say for instance, we can compute the average GPA for all the students. Each student will contribute with its own GPA, but if you wanted to compute the GPA for all the students, then we need to add up all the GPAs and divide by the number of students. Or if we wanted to compute the average time in the system for all entities, we would need to add all the time in system for each one of the entities, and then divide that total of time, summation of times for all the entities, divided by all the number of entities that contributed with that data, to estimate an average number for the time in system. So these are entity-based statistics because each entity holds its own value, and we want to be able to use those values as an estimator for an average entity. The other type of data is a time-based statistics, and in this case what we want is to estimate an effect through time of different stages of the system. So in order to compute what is the average number of entities in the system, for instance, we would need to have a weighted average of how many entities were there per time, and that is how we compute it. The event types, we will have arrivals, departures, the start of service, and the end of service. And those are the essentials of simulation, and we will see more in detail in the next video.